All right, so this is the experiment we're going to be doing tonight. So stoichiometry, you're probably familiar with. Single replacement is probably a new thing. So that is one of the series of reactions that's in experiment 5 that I haven't decided when exactly we're going to do, but we'll explain what a single replacement is. It's fairly straightforward. So let's go. There we go. So this experiment is pretty straightforward. We're basically just doing one reaction. And what's going to happen is pretty cool, actually. So we take some copper sulfate and copper 2 sulfate, which you should have in your bottle. So copper 2 sulfate. Anyone tell me what the formula for copper 2 sulfate is going to be? I've got copper and I've got sulfate. What's going to be the formula for copper 2 sulfate?
Two copper for one sulfate.
Nope.
CO2 SO4.
Copper is Cu. So if it's copper 2 sulfate, what's going to be the charge on copper?
2.
What 2? Plus 2 or minus 2?
Oh, plus 2.
Plus 2. What's the charge on sulfate ion?
-2.
Yep. So it's going to be the formula for copper sulfate.
Yeah, that's what. That's what I was trying to say. Cu2 SO4.
Nope.
Really?
Remember, you need to balance the charges. What's the simplest way to balance the charges?
Oh. Oh, you just leave it like that.
Right. It's just CuSO4. So this is going to be in solution. So we're going to have a 1 molar solution of that. And hopefully everyone knows what that means. And we're going to put in it aluminum foil, which is just aluminum. And what the single replacement is actually the aluminum is going to swap places with the copper. So in other words, the copper is going to become a metal and the aluminum is going to become an ion. And when aluminum becomes an ion, what charge does it have? Remember, aluminum is one of the rare.
I believe it's +3.
It is +3. So that's the single replacement, is that copper and aluminum are going to swap places. Aluminum starts with no charge as a metal, and copper starts with a +2 charge as an ion. And then they're going to swap places, and then copper is going to become just copper with no charge, and aluminum is going to become an aluminum ion, aluminum +3. So what we're going to be doing is we're going to be balancing that equation. We're going to be figuring out what the limiting reactant is. Oh boy, everyone wants to do that. And then hopefully, since you've read all this already, and we're just tested on it, we're going to figure out what the theoretical yield is. Because in the real world, you're not going to get 100% of the product out, right? I mean, that doesn't happen. Although you will find that some of you will get more than 100%, which doesn't seem possible, but we'll discuss some of the ways that will be. So we're going to balance this reaction. We're going to figure out who the limiting reactant is. What are our 2 reactants in this reaction?
Aluminum metal and copper sulfate.
Right.
Solution.
What are our products going to be?
Copper's solid and aqueous form of aluminum sulfate.
That's right. Excellent. So we're going to figure out what our yield is. So which product are we going to measure? Are we going to measure the amount of aluminum sulfate produced, or are we going to measure the amount of copper produced? Which one is it going to be? We're going to measure the mass of something. Is it going to be the mass of the copper metal, or is it going to be the mass of the aluminum sulfate?
Measure the mass of the copper.
That's right. Because the aluminum sulfate is going to be in solution. So it'll be very difficult for us to measure that. And then we'll just calculate the yield of our reaction. Okay. So this is just basically just goes over what I've been telling you folks like since the class started. How are we going to solve these stoichiometric equations? And you can see that a lot of what's said here is basically what I've been telling you from the beginning, with one big difference. And that is we need to balance the electric charges, because we haven't really been dealing with a lot of those kind of reactions. And this particular reaction involves electrons going from one element to another element. And so there's going to be changes in charges taking place during this reaction. And we have to balance those charges when we balance the equation. We're going to figure out how many moles there are of each reactant, figure out which one is limiting, figure out how much product the limiting reactant is going to allow us to create, and then we'll use that to determine our theoretical yield. And then once we finish the experiment and dry out the copper, we'll figure out what our actual yield is, and then work on the percentage. So notice here, the stuff I've been like whining about all term, always have units. Yeah, right. Check that the units cancel properly. Like I've been telling you, that's basically what I mean by never divide. Always multiply and make sure your units cancel. Give the answer with units on them. Yeah, kind of mentioning that. And not just avoiding rounding numbers too much, just don't round them at all if you don't have to. And wait till the final answer before you give your significant digits. So that should be pretty much spot on with what I've been saying so far. So this is an example of a reaction that was given in your instructions, where you have the same sort of replacement reaction. We've got magnesium metal swapping places with hydrogen. So magnesium is a free metal with no charge, and hydrogen is a +1 when it's attached to chloride ion. And basically they swap places, where magnesium then goes into solution with chloride ion, and hydrogen is released as a gas. And this is the sort of reaction we would do when we're calculating the value of R, actually. That is one of the experiments we did last term, was determining the value of R based on this very reaction by measuring the volume of hydrogen that's released. So in this, we have that much magnesium, which gives us this many moles of magnesium. We have 100 mils of half molar, which means 1/2 of a mole per liter. So we have that much HCl. So which one of these do you think is limiting? How would we determine which one is limiting?
Is it magnesium?
Sorry?
Is it magnesium?
How do we determine that? There's less magnesium. There's fewer moles of magnesium. Is that the whole story?
Yeah.
No, it isn't. How do we determine what a limiting reactant is?
Compare how much product, or is it product, will be made from the reactants.
Exactly. Yeah, we need to figure out how much product would be made. And in this instance, we want to figure out, since it's kind of hard to measure the concentration of magnesium chloride, it's much easier to measure the amount of gas released. So how much hydrogen H2 gas would be made if we converted all the magnesium, if the magnesium were the limiting reactant? How much gas would we make? How many moles? So I've got 0.0424 moles of magnesium. What would I multiply that by to figure out how many moles of H2? How do I convert moles of magnesium to moles of hydrogen gas? No one can help me.
Wouldn't you do a ratio of the moles of magnesium chloride to the moles of magnesium?
No. I don't care what the moles of magnesium chloride, because I'm not going to be measuring that. I need to know what the relationship is between moles of magnesium and moles of hydrogen gas.
1 mole of magnesium to 1 mole of hydrogen gas.
Right, it's 1 to 1, right? So so this is the unit I want to get rid of, and this is the unit I want to remain. So I have 1 mole of H2 for every 1 mole of magnesium. Cross out my magnesium, I'm left with moles of H2. So I would get the same number of moles. So that's how many moles of H2. If all the magnesium was converted, that's what I would get. Now, what about HCl? So I've got that many moles of HCl. Now, if all of that was converted to product, how much gas would I get? What do I multiply that by?
1 mole of hydrogen gas to 2 moles of hydrogen chloride,
Right,
hydrochloric acid.
right, because there's a 2 here. That's the whole point of having the balanced reaction. So I would get less. So if all the magnesium was converted, I would get that many moles. But if all the HCl was converted, I would get this many. So which one is the limiting reactant?
Hydrochloric acid.
Right, the HCl is limiting because it makes less product. So that is also our maximum yield. So our maximum yield of H2 is going to be 0.025 moles of gas. And so when we measure, when we're collecting gas, we measure its volume. And so it's about 22.4 liters per mole. So this is what we would expect to collect. We would expect to collect about 560 milliliters of gas. The way we collect gas is we just fill up a tube with water, and then we have turn it upside down, and then we have a rubber tube or a bit of hose or whatever coming out of our reaction chamber, and we put it into the tube filled with water, and the gas just displaces the water. So it's just like filling up a tube, only upside down, because liquid obviously flows down and gas will flow up. So that's how we would do that. So then we would just figure out how much gas we collected and then compare it to that amount. So if we actually only collected 490 milliliters of H2 gas, and the maximum amount we should have collected is 560 milliliters of gas, then our percent yield is 87.5. But in this instance, that's an error, isn't it? What should the answer actually be? This is taken directly from the lab instructions, and it's wrong. I just noticed that. What's the actual answer?
88%.
That's right. Exactly. It's 88%, not 87.5, because we only have two significant digits in both of those numbers. Very good. All right. So this is the reaction we're going to be doing. So aluminum metal and a solution of copper 2 sulfate. So we're going to get copper metal and a solution of aluminum sulfate. So we're going to add a little bit of sodium chloride, just a little bit of salt, just regular table salt. Now it's going to be added to the reaction as a catalyst. What does that mean?
Speeds up the reaction.
It speeds up to the reaction. You know what else? So what happens to the catalyst? Is it part of the reaction? Does it form part of the product? Are we going to see sodium chloride as either a reactant or part of the product?
No.
No, right. Part of what a catalyst does is it doesn't change. It may change during a reaction, but it'll go back to being whatever it was at the end of it. So whatever catalyst we throw into a reaction, it'll be there at the beginning and it'll be there in the same form at the end. So they're important that it speeds up the reaction. What chloride does is actually helps remove a really thin layer of aluminum oxide on the surface. So it pulls some of that aluminum oxide off, and then you get pure aluminum metal, which then allows the copper to react with it. So that's really all it's doing. So we don't really need to measure the amount of it very precisely. We just need to have some around for it to happen. So how are we going to balance our reaction? What are the two reactants again? For this particular reaction, what are our two reactants?
Aluminum and copper sulfate.
So how would I write that down? How do I write down aluminum as a metal?
Al solid S.
Right, and our other is copper sulfate, and we already agreed that that is CuSO4. So what are our products going to be?
Cu solid plus aluminum sulfate aqueous.
And what is the formula for aluminum sulfate? If aluminum is +3 and sulfate is -2.
2.
What's going to be the formula for aluminum sulfate?
2 aluminum to 1 sulfate.
Nope. That won't balance. And we have this, we have to have the same number of positive and negative charges.
Two aluminum to 3 sulfate.
Right. We just crisscross them. That's the pretty much the easiest way to do it. So 2 aluminum, 3 sulfate give us +6 and -6. So that would balance. So how do we start balancing this equation? Because it doesn't look balanced to me. How are we going to do that? So I have too many aluminums and too many sulfate ions as products. So how do we start balancing this? Oh, and this we should put aqueous and aqueous. So how do we balance this? What's the first thing we should balance?
Would it be the aluminum?
We can balance whatever we want first. We can start with the aluminum, sure. So how would I balance that?
For the reactant, you would put 2 before the aluminum.
Okay. So that balances my aluminum. Now, what about, I have too much sulfate ion as a
You
product.
would put a 3 above the copper sulfate.
Right, so that balances my amount of sulfate ion.
And then the copper on the product side would be 3.
Right. So that's our balanced reaction. That gives us 2 aluminums on each side, gives us 3 coppers on each side, and 3 sulfate ions on each side. Remember, these are a lot easier when you remember that sulfate ion stays together. We don't need to balance the sulfur and the oxygen separately. It's one thing. It's a polyatomic ion. So when we have a look at this, one thing we should think about is that nothing actually happens to the sulfate ions in this reaction. Because remember from the one of the questions on your exam, if I have copper sulfate, when I dissolve that in water, what do I get? I get copper ions and I get sulfate ions. And they go off their merry way and interact with water. And the same is true with the aluminum. When I dissolve, when this aluminum sulfate is formed, I'm going to have aluminum ions and I'm going to have sulfate ions. And so what's actually happening in this reaction is that we can take the sulfate ions actually out of it, because the sulfate ions don't actually do anything. So when you look at what's actually happening, this is the real reaction. And when we look at it that way, we can see that our charges balance, right? Because I have a +6 charge as reactants, because I have 3 moles of copper +2 going in. And then I have 2 moles of aluminum +3 coming out. And so that is the actual reaction, is that aluminum is giving, these 2 moles of aluminum metal are giving 6 electrons to 3 moles of copper and changing those 3 moles of copper +2 ions to 3 moles of copper metal. So that is actually the reaction going on. And we call this a redox reaction or an oxidation reduction reaction. Remember, we talked about that a little earlier, where the aluminum is being oxidized. The aluminum is going from having a charge of 0 to having a charge of +3. It's being oxidized. Meanwhile, copper ion is being reduced because it is going from a charge of +2 to a charge of 0. So this is an oxidation reduction reaction. So, and these are the molar equivalents we're going to be using for our balanced reaction. 2, 3, 2, 3, and 2. So remember that when you balance the equation, that's how we're going to do it.
So we don't need to write sulfate.
No, sulfate is in there.
Oh, okay.
Yeah.
I just want
No,
to.
I'm just saying that the sulfate doesn't actually participate in the reaction at all,
Oh, okay.
because the sulfate ion is there at the beginning of the reaction and the sulfate's there at the end of the reaction. It didn't do
Okay.
anything. We call that, in chemistry, we call that a spectator ion, which is kind of self-explanatory, right? It just basically sits around and doesn't do anything, just a spectator on the sidelines. So these are the stuff we're going to need. So find your, hopefully you've already found your copper sulfate, some aluminum foil. If there's none in your kit, it's hopefully you get some in the house somewhere. We're going to do some filtering tonight. So we need a funnel and some paper. We're going to use our 50 ml graduated cylinder, a balance, some pipettes, spoons for stirring, weigh boats, plastic beakers. We're going to do the reactions going to take place in a plastic beaker. As I mentioned, you're going to need some table salt. So you don't need a lot and you don't really need to measure it. Basically just a pinch of salt. So we're going to measure 50 mils. Oh, sorry, 100 mils. So 100 mils of the copper sulfate and put it into the 250 ml beaker. So if we have 100 milliliters of 1 molar copper sulfate, how many moles of copper sulfate is that? To put it another way, if we have 1 mole per liter of copper sulfate and we have 1/10 of a liter, how many moles of copper sulfate is that? Should need a calculator.
Is that 1/10?
Yeah, 1/10 of a mole, right? So if we have 1/10 of a liter and it's 1 mole per liter, that's 1/10 of a mole. So that's how many moles of copper sulfate you're going to have. So you're going to put 1/10 of a mole of copper +2, excuse me, in a reaction. Then using a ruler, you want a 4-inch by 12-inch piece of aluminum foil, okay? So you're going to want between 1.4 and 1.6 grams of aluminum foil. So somewhere in that range. And then we're just going to tear it up into, or cut it up into little pieces, okay? And then add them to the reaction after adding a little bit of salt. So what's going to happen is this is going to heat up. This reaction is going to heat up. So take a plastic spoon, you're going to mix in the aluminum foil. The aluminum foil is going to go into solution. It's actually going to disappear right in front of your eyes. And you're going to get this really ugly brown precipitate forming. That is the copper metal that's falling out of solution. You're going to notice a color change because copper sulfate is this lovely blue color. Copper 2 is blue. And copper metal itself is brown. So that is one of the hints that there is a reaction going on. What are some of the other hints that there's a reaction happening?
Temperature will go up.
Temperature's going to go up. Temperature's going to go up a lot. So what kind of reaction is that?
Exothermic.
Which kind of thermic?
Exothermic.
Right, it's exothermic. It's going to be releasing heat. So it's going to, don't worry, it's not going to melt the beaker or anything. Yeah, just be careful you don't spill it. So the aluminum foil is going to float on the surface. Just keep poking it down with your spoon, and just keep stirring it to expose all the aluminum until all the aluminum disappears. And so since all the aluminum disappears, what do you think is going to be the limiting reactant? If all the aluminum goes into solution, which one do you think is the limiting reactant?
Wouldn't it be the aluminum?
Yeah, probably. So we need to check, but we're going to need to check that, right? So it may be the limiting reactant, it may not be, but it probably will. Because if it wasn't the limiting reactant, we would have aluminum left over, right? So, but we do still need to do the calculations. But more than likely, that's going to be your limiting reactant. So then we're going to let that react for about 15 minutes or so. And then we're going to filter. So just like coffee, and basically the filter we're using is basically the same material as a coffee filter. We fold it once in half, and we fold it again in half. I don't really know what this, it says to tear off a piece. I don't really know if that's necessary or why they're doing that, but you know, you can try that if you want. Basically, we're just going to form this little cone and then put it in our funnel, and then pour the product over it, and then basically rinse it several times with water, because we want to break up whatever is in there. We want to separate our solid copper product from whatever else might be in there. So what else is going to be in that solution that the copper's in? So here's what that's going to look like. We're going to be filtering. So this is our product here. And then we're going to be filtering it over here. What else is going to be in there? What else is in that solution that we need to get rid of? So you've just done a reaction. One of the products is copper metal. What's the other product?
Aluminum sulfate.
So where's that going to be?
It'll be in the liquid form.
Right, it'll be in the liquids. That's why we're filtering it. What else is going to be in the solution? Not just aluminum sulfate. What else is going to be in there?
The salt.
Yeah, there's going to be some sodium chloride. And what else?
Copper sulfate.
Exactly. There's probably going to be some copper sulfate left over. Since more than likely the aluminum is going to be the limiting reactant, we're going to have excess reactant left over. And we want to filter that away too. Because if we don't filter it away, when it dries, the mass of our product is going to be the copper plus whatever copper sulfate was still around, plus the sodium chloride, plus the aluminum sulfate. All those things are going to be there. We want to rinse all of that away. And so all we're going to have left over, hopefully, is copper, metal, and water. So then, once we've rinsed it a few times, then basically we're just going to let it dry. And you can either put it in the oven and dry it at very low temperature, like 150 or 175, or you can just leave it overnight. Just let it dry overnight. Just put it on some paper towel and let it dry. Okay. So then when it's all dry, we measure the amount of product we got. So this is basically the only data you have to collect for this reaction. Write the balanced chemical equation. We've done that. What's the volume of solution we used? Our mass of tinfoil. Calculate the moles of each one. Calculate the moles of copper you should see. This basically will be our theoretical yield. Determine what the limiting reactant is. Figure out the theoretical yield of copper in grams, because that's what we're going to be measuring. Our mass is going to be in grams. It's not going to be in moles, right? Because we can't measure in moles. Grams we can measure. So that will be the actual yield you get in grams, whatever it is you measure. And then calculate your percent yield of copper. So if your yield is over 100%, what was the mistake? What was the error in your experiment, do you think?
You weighed it wrong, or
No,
you added some. Oh,
probably
really?
not. That's probably no. I mean, most people can weigh things fairly accurately.
Oh, incomplete drawing.
Yeah, that's a big one. Exactly. There's still a bunch of water in there. So that's probably the most likely source of error. Other one, and then you'll have to figure out and there's some other ones too. You may notice when you're drying it, that some of the copper that started out being brown will turn color and will become blue. I'll leave it up to you to figure out what that means. Okay. Anyway, so why don't we get our stuff together? Cameras on, goggles on, and we'll get started in about 5 minutes. Any questions about the?
Yeah, Professor, I wanted to actually ask you, when you were doing the calculation to figure out the moles of hydrogen gas, why didn't you try to figure out the moles of the other product, the magnesium?
Because we weren't going to be measuring that.
Chloride.
Because we weren't going to be measuring that.
So in this theoretical sample question, they wanted specifically the one that was the gas product.
Right, because that's the one we're going to be measuring. Same with this reaction. We're not going to be measuring the amount of aluminum sulfate produced because we have no way of figuring that out. What we can figure out pretty easily is how much copper metal is made, because we can separate that we can easily separate that with a filter. That's easy. But trying to measure the amount of aluminum sulfate would be really hard to do, because we'd have to separate the aluminum ions from whatever copper ions were in there. We'd have to separate so that would be really hard to do. But just measuring a solid, real easy.
Okay.
Okay. Okay. So 5 minutes, then we'll get started. All right. All right. So everyone start with, well, goggles on. You get the goggles on. Excellent. So try and put as precisely as 100 milliliters of our blue copper sulfate in the reaction in there as possible. And then remember, you're going to want that's just a little pinch of salt. I don't even think you need to measure it. Just a half a spoonful of salt. and then mix it up, make sure they get the sodium chloride dissolved in the solution. And then remember, we want little pieces of aluminum between 1.4 and 1.6 grams. So basically, you just tear little pieces out and just keep adding them to the scale till you get between 1.4 and 1.6. Oh, Cassandra, I love the angle you got there, man. That's awesome. You can see the whole thing. Cool. So you get this round, rather heavy piece of filter paper. So the simplest way to deal with this, probably not the best way, but the simplest way is to just fold it in half once, fold it in half twice, and then you make a cone. Where basically there's three folds on one side and one on the other, which isn't a very good use of the filter paper, but it's easy. So then you'll notice if you put it in this funnel we have is fairly small. And if you put the filter paper in it, it just pops right out. So what you want to do is put a little bit of water in there to keep it from moving. Just put a little bit of water in there. It'll basically help the filter paper stick to the funnel. If you want to get fancy with the filter paper, you could make a flute. Which basically means you just fold them in half again. So for those of you who are into origami, you might enjoy this. But yeah, the paper's kind of thick to do that. Yeah, so just pop it in the cone, put a little water in there to get it to stick. Basically, whenever you're doing any kind of filtration, you always want to add a little bit of water first, or whatever the solvent is in your solution, to help it, because this will work better when it's wet. And then once you've poured it in there, just keep adding water to the copper, because you're not going to get all of it. Just keep adding a little bit of water to it, swirl it around, and then dump it in. Add a little water to it, swirl it around, dump it in, because you want to recover as much of that copper as you possibly can. Oh, and there's a lot of questions in the report document. So make sure you follow that as well, because there's a bunch of questions basically about like what you've seen, observations you've made, that sort of thing. So always a good idea when you're doing these sort of reactions, just write down any observations you have. Like we noticed, it made a noise. Write that down. It got hot. Write that down. There was a color change. Write that down. All that stuff. Because, you know, as scientists, and then later, you know, wherever you're going to be working in the future, there's always going to be record keeping. It's going to be super, super important, because when something bad happens, like in the hospital, something, you know, some patient, you know, develops complications from something, everyone's going to want to figure out where did that come from. So everyone's going to want to check, you know, whoever came in contact with that patient,
EYA,
they're going to want to check.
cover your
Yeah, well,
ASS.
they want to, well, not just that, but I mean, yeah, obviously we all want to do that, but we want to find out what the hell happened. So, you know, did we miss something? Was there, did the patient have anaphylactic reaction to antibiotics that we should have noticed? Maybe that, you know, they should have had a medic alert bracelet and they didn't have it on or something. All kinds of things. So notes, sort of taking meticulous notes about what happened, is not only is it a way to sort of figure out what happened when it goes right, but it's even more important to figure out what happens when things go wrong. So if you find out that you got, you know, let's say you're pouring your product solution in here and some of it spills, well, what's going to happen? Write it down, you know. Or some of it, like maybe you didn't fold this properly and some of the solid got past the filter and then went into the you know, 50 mil column. That's fine, you know, write it down. Of course, if that does happen, you can always just put a little bit of water in here and then just pass it through again. You can filter this as many times as you want.
Professor,
Yes.
what does it mean to decant the solution into a plastic cup?
Decant. So decant means if you have a solution with a solid in it, basically what that means is you just slowly pour out the liquid while leaving the solid behind. So you just pour out as much of the liquid as you can, because basically there's no need to filter that because there's no solid in it, so we don't really care. So just decant as much of that into another container as you can without losing any of the solid. And if you lose a little bit of the solid, write it down. Yeah, that's all decant means. If anyone's had like a really old bottle of wine, solids will fall out of it over time, and so you'll get this, like, you know, residue precipitate at the bottom, and you don't want to drink that, so you just sort of slowly pour it out. It builds up over time. So that's what the wine decanter is. You basically empty the bottle into a bigger container where you can let the stuff filter or settle to the bottom a little more easily.
Does it have to be pure water specifically?
Yes.
Oh, is bottled water okay?
Oh, fine. Yeah, totally
Okay.
fine. Yeah, I just use filtered water. I got a Brita upstairs. I just use that. I mean, ideally in the lab, we use not only distilled water, we use deionized water as well. But trying to find deionized water is kind of hard. So like we have these big machines that basically distill water so that it's clean, and then we deionize it so it doesn't have any sodium or potassium or chloride ions or calcium or anything. And then we filter it one last time to get rid of any organic compounds, like anything containing carbon. So we pass it through an activated carbon filter to get rid of all that stuff. And that's basically the cleanest water you can find. We'll just make do with filtered water. So has anyone started filtering yet? Sanders filtering. There you go. Yeah, so be careful. One of the things that can happen is that this is going to be really top heavy when you've got the filter in there and you've got liquid in there. And so you're going to have a whole bunch of weight on the top, and this is made of plastic, so it doesn't weigh very much. So like either keep a hand on it or just put some stuff on it to weigh it down so it doesn't tip over. So Megan, did you decant that first? Did you just let the copper just fall to the bottom? You did? Okay. Cool. Yeah, so has anyone noticed what the color of the filtrate is? So once you've passed stuff through the filter, what goes through is called the filtrate. So what passes through it? Anyone notice what color that is? I could really see it well, Megan's, with the way your kitchen's lit up or something. I can really see the color well. So what color is it, Megan? The liquid.
Sorry. Oh, the liquid or in the
The
funnel?
liquid.
It's like light blue
Yeah. Why do you think that is?
because it's taking all the filter paper is like pulling the copper from the water and letting all the rest of the liquid go in.
Well, what do you think is in that liquid?
Oh, the copper sulfate.
That's right. That's right. So basically that sort of lets you know that the copper sulfate is in excess,
Okay.
because if it wasn't, we wouldn't see that blue color anymore, right? Basically, we would have converted all of that copper 2, which is the ion that makes that color. We would have converted all of it into solid copper, but we didn't. And so that is your excess. That's the excess reactant. That's like, that's sort of clear evidence of that. One is that all of the aluminum was consumed. So that sort of let us know that that was the one that was limiting. And 2, we see that there's blue copper 2 left over. And if it's left over, it's in excess. And if it's in excess, it can't be the limiting reactant.
Okay.
Yeah, so you could, yeah, that's a really pretty color from here.
Thank you. Did it myself.
Yeah, so just you can so before it crawls all the way up to the top, once that liquid hits the bottom of your funnel here, it's basically going to stop running. So just you can dump that down the sink with a little bit of water.
Okay.
Let me have it. We'll dump it out and then you can put the rest in.
Oh, this stuff.
Yeah, he said just dump it out, right?
No, it's just copper sulfate. You can put it on your plants if you want.
Oh,
I'll dump it out.
thank you.
Copper is actually an essential element, so no, there'd be no harm putting that down the sink. The fish will thank you.
Wait, but didn't the thing it said that it's dangerous to aquatic life though.
Copper
So how's it
sulfate,
possible? Yeah.
if it's too concentrated, yes.
Oh.
Yeah, so like a really high concentration of anything is not good. But it gets diluted like many trillion fold. So yes, you don't want to drink this. certainly. But you actually do need a little bit of copper in your diet.
Professor, I have a question.
Yep.
So when we're wetting this, do we like wet the whole thing or we just like dab it a little?
Oh, so you fold it first.
Uh-huh.
So you fold it first, and then you put it in the funnel, and then you wet it.
Okay, thank
Yeah.
you. But do we wet the whole thing? Or like, do we only put like how much water do we put in it? Do we only put like a little bit?
Yeah, just enough for it to like basically stay in place.
Okay, thank you.
Yeah. Yeah, water goes through this fairly easily. And I guess Renee's getting the last little bits and pieces out of there. So everyone's filtering now, I'm assuming. Actually, all I can see of Marla's is just, oh, you're gonna start filtering now, right, Marla? There you go. Yeah, so pour out, if you've got copper on the bottom there sort of settling out, you can just pour out a little bit of that liquid. As long as it doesn't have copper in it, you can decant that. You can pour that to waste.
So so it says rinse it with about 20 ml of pure water.
Mhm.
And so I
Yeah,
did that,
that's
and then it says
about.
in
I mean,
the-
it's just, yeah, just basically just keep adding water to it until there's no more blue color coming through. That's basically what you're looking for. You want to separate the copper from the copper too.
and then it says transfer it to the filter funnel, and then you know how the funnel has a hole. So where do we put the funnel on top of the beaker or on top of the plastic cup?
On top of the 50 ml cylinder,
Okay.
just like you've got it right there.
Okay.
Yeah. Yeah. So did you put a little bit of liquid in the on the filter paper first, Vera? Just
Yeah.
put a little bit of water on it.
Yeah.
Okay, good. Yeah, because it looks like it's staying in place. So. Oh, Amy, you got your camera fixed.
Yeah, I was using my laptop and now I'm using MacBook.
Yeah, that's really clear. That's a really sharp picture.
Is this correct? I don't know what I'm doing.
Yeah, that's exactly doing it perfectly. Yeah, so that, since you notice that the liquid that's been filtered through is blue, right? So why is that?
That's the limiting reactant, or
Nope.
that's the limit.
No, what's making the blue color? Remember?
Copper sulfate.
Right. So is it the sulfate or the copper that makes the color?
Sulfate.
It's
Or
not the sulfate.
copper.
It's the metal. Yeah, I mean all of the pretty colors we see in a lot of the colors and paints and all that stuff. That's all metals. It's metals that are basically responsible for making those colors. And so copper 2 is this really pretty blue color, and copper 1 is green. That's why, remember, we were talking about the Statue of Liberty being green because she's been oxidized over time with oxygen and turned into copper 1 oxide. That's the green color. So basically we want to just keep filtering our product until we no longer see any more blue coming through. So basically we put water goes in, water comes out. Once we get to that point, we're done. And then we can just let it dry overnight.
Do I let it dry like this? Like pour the blue out and then just dry like that?
You know, just take that out and then just put it on some paper towels and just put it somewhere dry.
All right.
Professor, I can empty this. You said down the sink after I
Yep.
filtered it.
Yeah,
Okay.
all the chemicals that we're using this term can be disposed of that way. Yeah. 'cause
Got it.
there's-
And then
There's,
what about
there's
this?
nothing dangerous.
Okay, and I'm just rinsing it until it completely runs clear, correct?
That's what you, yeah, that's basically what we're shooting for.
Got
It
it.
doesn't say that in the instructions, but that's basically what we want to do. Because if all the blue color is gone, that tells us all the copper 2 is gone. And if that's gone, the sulfate is probably gone too. And probably all the aluminum 3 is gone as well. So it's basically, we would say it's an indicator that all
Got
the
it.
ions are gone. We want to get rid of all the ions, and all we want left is the metal.
Got it. And then the solution that we had previously that it told us to empty into the cup, also dispose of that. No need to
Yep.
keep that.
Mhm, yeah.
Okay.
Yep. I mean, if you wanted to do it again, you could just throw some more aluminum foil in there and watch it happen all over again. But you know, do we really want to do that? And so if anyone, so yeah, so I would just then make sure, so you unfold it. Because you want it, so when you've got your product on the filter paper, unfold it so you expose as much of the copper metal to the air as possible. Sort of like, you know, spread it out a little bit so it'll dry faster. Put it on some paper towels, so because water is just going to soak right through this to whatever it is. So just put some paper towel under it and just put it somewhere safe and dry. Like maybe in a, just up high somewhere. And if you do actually want to put it in the oven, I wouldn't put the temperature up more than about 175 or so. So then write down tonight what the color of your product is, or you can even take a picture of it. That'd be cool. Take a picture of it tonight, and then take a picture of it in the morning and see if it looks the same. And if it isn't, that should go into your report as what you think happened. Yeah, this is the exciting part, watching it filter. It's about as much fun as watching paint dry. Pretty much all done there, Renee?
Professor, I have a question.
Yeah, I think so.
All right, cool.
Do we pour all of this out? We filter it all out?
So you want to decant it first, meaning you just pour off whatever liquid you can slowly without disturbing the precipitate, without disturbing the solid metal. So do that first. That'll help your filtering go a little faster.
Okay.
And then, yeah, then all of it goes over the filter. Yep. Yeah, so basically tomorrow or tonight, whenever you're going to do it, calculate the moles of aluminum, balance your reaction, figure out how many moles of copper that would produce. Then can figure out how many grams of copper that would produce. That's going to be your theoretical yield. So then if you get under the theoretical yield, which you should, just give a percent. And if it's over, think about some of the reasons why that might be. And we sort of talked about some of them tonight. It's not dry. Maybe you want to let it dry a little bit longer and then measure the mass again. Or when you're transferring the metal off of the filter paper, maybe there's still a bunch of it stuck on the filter paper. That could be. Or maybe there's some filter paper mixed in with your product. That can be too. So there's all sorts of things. And that's part of writing the report, is figuring out sources of error. And when scientists talk about source of error, we're not saying that we did something stupid, although I've done plenty of things that are stupid. But parts of the experimental protocol that we don't say it goes wrong, just things that can easily be traced back to as a possible source of error, like too much water in the product. That's not your fault. That just happens. Maybe there's some, little bit of paper in your product, and you can't really separate it out. Just write that down. That's not your fault. That just happened. These things happen. So when we say sources of error, we're not saying like, with the big finger pointing blame. We just want to know what parts of the experimental protocol could have led to a non-optimal outcome. I'll just put it that way. So it is quite possible that some of you are going to have over 100%. Don't be surprised when that happens. Just try to explain why that could be. That's more important than making a mistake is realizing the source of it, identifying it, and then correcting it next time. That's much more important. Because all good scientists make mistakes. Great scientists figure out what they did wrong and then they fix it next time. Some of us never figure it out. All right, so anybody else have any? So it seems like everyone's doing the filtering at this point. Reactions are all done. Did anybody have any aluminum left over? Or was all of it consumed in the reaction? Did anyone notice any shiny stuff when you're filtering? Anyone notice anything shiny? Good. Because that would be something to write down. If there's just, because as you can see, copper ain't very shiny, Once you get enough of it together, smush it together and polish it, it can be kind of shiny, but even then, at the best of times, copper is pretty drab.
You said to use 150 degrees on the oven.
Yeah, pretty much whatever the lowest setting you have.
Okay.
And just let it go for, I don't know, a couple hours, and then check it.
On the paper, it said don't exceed 250, but they said preheat the oven to 225 Fahrenheit.
Oh, 225? Okay. Oh, Fahrenheit. Yeah, duh.
And then heat it for about 25 to 30 minutes.
Wow. Someone who read the instructions. I read the instructions too. I just didn't remember that part. But
So if you don't see any, if you see clear water, then
Mhm.
that's good. Because that means there's no more copper sulfate.
Yeah, it would mean you're probably done. So
Okay.
how many times have you added water to it?
Quite a few times, only because I see tiny bits in the beaker of the copper sulfate.
Oh, you still see some blue in the
No, I
in the
mean,
filter?
I still see the brown. When the aluminum turned brown, I still see bits of that. So I'm trying to get all of the.
Well, that's not the aluminum turning brown. That's the copper coming out of solution. Yeah. The brown is the copper. So you still have some in the original reaction vessel. Yeah, you just want to rinse that. Just put some water in there, shake it up, and then filter it. Yeah, you want to do that fairly quickly. When you shake it up, you want to fairly quickly just dump it in, because it'll just, the minute you stop swirling it, the copper is just going to sink to the bottom again. And you basically you want to suspend it. You want to make a suspension, and then bam, just pour it in there.
Professor, I have a question.
Mm-hmm.
So when I filtered it out, my solution was clear. It wasn't blue.
Really?
I don't know how.
What was the mass of your aluminum?
1.42.
Oh, interesting.
I don't know why no color is
That is weird, because yeah, so how much copper sulfate did you add? Was it 50 or 100 mils?
100.
Huh,
Yeah. I'm
That's-
confused right
that's
now.
really strange. So there's none at all, no blue color at all.
No, like I don't know if you can see it right here. Like it literally has no color to it.
No, that is clear as anything.
Yeah, it looks like water.
So what is the, on the, and there's no shiny, there's no aluminum left over?
No, when I filtered it out, all I got was like this stuff. And if you can see.
Okay, yeah, you still have a bunch of product there, so.
Yeah, so
Yeah, so
but
you want to rinse that with what, but that's really odd. Yeah, write that down. So what, on the bottle, you still have the bottle of copper
Yeah.
sulfate? So what
Yeah.
does it say on it?
copper sulfate 1 m.
Huh,
All right, it's right here.
1 molar, so
1 molar, yeah.
weird.
Yeah.
Because everybody else's filtrate was blue, right? I mean,
Yeah,
everyone.
that's
that
why I
could
was
see.
confused because I was looking at everybody's and it's all blue and mine is.
Yeah, that's really weird. That's
Mine
really
wasn't
interesting.
super blue. It was like very faintly blue, and I just thought I just decanted it amazing, so that's probably why.
Okay. I mean, it could be. I don't know if all of these solutions were made at the same time in the same place. Some of these solutions are made from copper sulfate. And oh, on the bottle, does it say copper sulfate or does it say copper sulfate hydrate?
Just copper sulfate.
And on the side?
Oh, it says copper sulfate hydrate.
Okay, there you go. Well, that shoots down that idea. I thought maybe, so what a hydrate is, and this is the experiment I'm kind of surprised we're not doing, because it's really easy and pretty straightforward experiment to do. Remember I was telling you before that these ionic compounds basically are what we call hygroscopic. They pull water into them. And even in crystals of this copper sulfate, there's still going to be water in it. And so when we weigh out the copper sulfate, for every mole of copper sulfate, there's 5 moles of water that's bound to it intimately. So even when you dry it, there's still copper sulfate ion and water right in there. And so sulfate in particular attracts a lot of water. So I thought that perhaps maybe it was a different form of copper too, and maybe a slightly different color, but no.
Yeah, it's so
Yours
weird.
is the same. But that's an experiment that we did last term. So actually take a whole bunch of different ionic compounds that have different amounts of water bound with them, and you heat them up and drive off the water because they're not covalently linked. They're basically just really tightly associated. And you drive off the water, then you try and figure out what's the molar ratio of water to ion. But I don't think this kit came with that experiment, because if it did, we'd be doing it. All right, any other questions? Yeah, it's really interesting, Rajat. I would write that down.
Can I ask you a question regarding the quiz question? The pre-lab quiz question?
Oh, sure.
So for chromium and iodine, to
Mhm.
balance it out, so you know on the product side, chromium is chromium 3. So does that mean that on the reactant side, it would imply that chromium is also +3?
That's exactly what that means.
Oh,
So,
okay.
yeah,
Because
so
I had trouble trying to figure out the balancing it because I wasn't sure if that's what it meant or not.
yeah, so chromium, so solid chromium is just Cr. And then what's solid iodine? I think this is where a lot of people had trouble.
I with a S?
No.
Oh,
Now, the problem is, remember that this is in group 7, right? So all those elements in group 7, they don't exist as just simple, like, F, Cl, Br, I. How do they, in their most stable form, how do we find them?
oh, it's a halogen.
Right.
Okay. minus-
So fluorine gas isn't just F. What is it?
F minus 1.
No, that's fluoride ion.
Oh,
Or chlorine gas. What's the formula for chlorine gas?
oh, it'd be F2, right?
Right. They're all 2. F2, Cl2, Br2, I2. So solid iodine is I2.
Huh.
That's the trick to that one. So
Okay.
then chromium 3 iodide, so we know it's chromium plus 3. And what's the charge on iodide ion?
-1.
Right. So what's going to be the formula for chromium 3 iodide?
You'd need 3 of the iodine in order to balance
Well,
out the
iodides, since it's
iodide.
right. So that's CRI3 is the product. So we go back and we see that's the only product that was given, right?
Yeah.
And then we just balance the reaction. So I've got 3 iodines on this side. I've only got 2 on this side. So I put a 2 here and a 3 there. And then I just balance my chromiums, 2 and 2. And there you go.
Oh, okay. I didn't know that iodine in solid form had to have 2.
Yep. Yeah, because I by itself, remember, has 1, 2, 3, 4, 5, 6, 7 valence electrons. So that's going to be reactive as hell. That's going to steal an electron from somebody. And if the only other thing around is more iodine, it just 1, 2, 3, 4, 5, 6, 7 just forms that single bond, and they're both good to go.
Oh, okay.
Yeah.
Would it be the same as I2? Would it be the same as elemental
Exactly. Yeah, elemental iodine is a solid.
Oh, okay.
And that goes back to what we're talking about with London dispersion forces, because I2 is a pretty big molecule. I mean, iodine weighs 126. So 2 iodines together weighs, something like 260 grams per mole. It's a pretty big molecule. And so that's big enough so that it can form enough London dispersion forces that it actually becomes a solid at room temperature.
Oh. Yeah, and isn't iodine really important? Iodide. That's really important for, for example,
Thyroid
I know
function.
there's radioactive iodine for people with thyroid cancer.
Yeah, that's what iodine's mainly used for in the body, is forming thyroxine, which is the hormone that your thyroid produces. I think it has 3, maybe even 4 moles of iodine per mole of thyroxine. There's a lot of it. And so basically, if you have thyroid cancer, they give you radioactive iodine, because what the iodine will immediately go to the thyroid. It concentrates in the thyroid and basically just irradiate the thyroid and destroy the cancer that's there. Unfortunately,
Depending on the type you
destroy
have,
your
I know
thyroid
that.
too.
Really, it does? I thought it wouldn't.
No, it
I know
destroys the
generally
whole thing.
surgery they would, but I mean, I have a friend who had a radioactive iodine treatment for cancer, and I heard she still has her thyroid and everything. I believe she has to take medication, but I don't remember.
So if we want to figure out our moles of expected product, you go right to the balanced equation. So we start with copper sulfate plus aluminum makes copper plus aluminum sulfate. Oop. So let's balance it. So we have 3 sulfates and 2 aluminums and 3 coppers. So I think that balances everything. So we so we start with like 0.1 moles of copper sulfate, right? So I think that's like 100 milliliters of a 1 mole per 1,000 milliliters solution. That's what 1 molar means, right? So that's 0.1 moles. And then the aluminum, you've weighed it. So let's say if you have 1.5 grams of aluminum, then you figure out, let's see, what's the molar mass of aluminum is 26.852.
92.
Is 1 mole. So that gives you moles of aluminum. So once you have moles of copper and moles of aluminum, convert both of those to copper metal by doing the molar ratio. For every 2 moles of aluminum metal, I get 3 moles of copper. For every 3 moles of copper sulfate, I also get 3 moles of copper. So that's just a 1-to-1 ratio. So figure out which one makes less. Which one makes less copper metal, copper solid with no charge? Because this is your product right here. To figure out which one makes less, I think you will find it's the aluminum that makes less.
Okay.
Because I think the experiment is designed to have copper sulfate in excess. So whatever the number of moles of aluminum you figure out, there will be a 3 moles of copper to 2 moles of aluminum ratio. So you'll make a moles of aluminum times 3/2. That will be your theoretical yield of copper. Okay, and then convert the moles of copper to grams, because that's what you're going to be measuring tomorrow, is the mass of copper you've got. Yeah, just so it all starts with the balanced equation. We can't do anything without a balanced equation.
Okay.
And then from there, how many moles of copper sulfate do we have? How many moles of aluminum do we have? And then figure out how many moles of copper product would that make? And I think you will find that the aluminum will make less. That makes it limiting.
Professor,
Yeah.
what did you write at the very bottom? It says 100 ml times.
Oh, 100. Yeah, so that's 100 mils of solution. And we multiply that by 1 mole of, so 1 molar, this is what 1 molar means. 1 molar means 1 mole
Okay.
over 1,000 mils, which is the same as a liter, right? So 1 molar just means 1 mole in a liter. That's all it means. So it just makes it easier to calculate that it's 0.1 moles of copper. That's what you're supposed to start with. I think everyone starts with the same amount of copper because everyone measured 100 mils of the 1 molar solution, but everyone's going to have slightly different amount of aluminum depending on how much you weighed out. So everyone's answer for their theoretical yield is going to be slightly different. It's going to be around the same number, but they're not all going to be exactly the same.
For the volume of the 1 molar copper sulfate, you want the answer in liters, right? Not milliliters.
Did you measure liters or milliliters?
I measured milliliters.
Well, then write that down.
Oh, okay. But I thought maybe you would want it in liters, so I just did dimensional analysis to
You can,
get it
if
in
it doesn't
liters.
say, if the table doesn't say what volume to report, if it doesn't give you units, you can report in whatever units you want.
Oh, okay.
You could report in quarts if you want to. Yeah, only worry about that if it tells you, like, like on a test or something, I want the answer in liters, or I want the answer in moles, or I want the answer in kilometers or something.
Okay.
If it doesn't say that, you can report whatever units you want, as long as it's a unit.
Okay.
Yeah. So yeah, so don't just put like 0.1 because you need to have a unit with it.
Okay.
All right. So Amy, is that good with as far as figuring out your limiting reactant and then amount of product? You think you got it?
For the, I got 2 moles of aluminum over 3 moles of copper sulfate, but I don't know if I'm doing this right.
No, that's right. But remember, you're calculating, let me just get rid of all this because you're calculating product. So oh, so 4, 3, right? So 3, 2, 3. Yeah. So what you're calculating is product. So this is your product right here. So you're going to start with moles of copper sulfate. And then you want to convert that to moles of copper. And so you're going to want to always have the moles of copper on top and moles of copper sulfate or whatever else you're doing on the bottom. And same with aluminum. So for my aluminum, I'm going to have moles of aluminum times equals moles of copper. How do I, basically you want to ask yourself, how do I get from moles of aluminum to moles of copper? So I want to put moles of aluminum on the bottom because that's what I want to get rid of. And I want to put moles of copper on the top because that's what I want. Well, what's the ratio of copper to aluminum? It's 3/2. So remember, when you're doing these unit conversions, always have the unit you want on the top. And the unit you want to convert goes on the bottom. So then you never mix up what the ratio is. Because it's really easy to make that mistake, right, Amy? I mean, I make that mistake all the time. Do I multiply it by 3/2 or do I multiply it by 2/3, right? It's really easy to make that mistake. So that's why I always say, include your units when you're doing the calculations, because if you include the units, then you won't make that mistake. But if you're just like multiplying by 3/2 or multiplying by 2/3 without any units in there, it's so easy to make that mistake. I do it all the time. That's why I go through that really long, arduous process of canceling units, because it's so easy to make that mistake. Yeah, I don't just do that just because I'm a bad guy and like to torture my students. I mean, I like that too, but it really helps in avoiding that error. Because I saw a lot of students on the test not canceling units, and a lot of them made mistakes when they did that. So all right, any other questions, folks?
Thank you, Professor.
Okay, no problem.
Thank you.
Sorry. All right, so everyone, yeah, dry your stuff out. I guess Renee's off to bake his. He said he's gonna set it. Are you baking it, Renee? All right, yeah, it'll be cool. I'll be interested to see if it looks any different. I'm always afraid of throwing things in my oven. I never know. I think it's gonna like pop open, and I'm gonna have copper everywhere, and then I'm gonna have copper in my food, and then I'm gonna get all paranoid. But don't let that be a warning to you. All right.
So I just want to make sure, for like, for example, the moles of copper sulfate, you just use whatever the mass of copper sulfate is
Don't need the
divided by.
mass. Don't need the mass.
You
Why
know,
don't you need the mass of the copper sulfate?
because it's in liquid form.
Not only is it in liquid form, it tells you what the concentration is.
Oh,
So by
It's
the
in 1
label
mole.
tells you right on it, it is 1 molar, which means there's 1 mole of it for every liter, meaning you do not have to calculate mass. They've already done it for you. They've
Oh,
already put exactly 1 mole of copper sulfate in 1 liter of solution. So you don't have to do that, which is
So you
very
just
nice
write-
of them, I think.
1 mole of copper sulfate over 1 liter.
Yeah, that's what it means. That's what 1 molar means, remember?
Oh, okay.
Yeah, so you don't have to do any of that calculation.
Oh, but for the aluminum, you would then.
Aluminum you do, right, because we
Okay.
don't
It's solid.
we don't buy aluminum by the mole. That would be a very weird way to buy aluminum foil. Of course, we don't even buy it by the gram either. We buy it by the foot. All right, any other questions? How you doing, Audrey? You look worried. You look freaked out. Are you okay?
I'm like a little worried about my volume of the copper this volume. The
Oh,
CSO.
did you have less than 100?
No, I did actually actually 100.
Oh, okay. So what's there to worry about?
So wait, I'm cool, like a little.
Oh, you're wondering how to calculate the
Yeah.
amount? Oh, okay.
One volume.
All right, let's, oh, trying to share a screen. There we go. All right, so yeah, so the calculation for number of moles of copper sulfate is really easy, much easier than the aluminum. So right on the bottle, it says we have 1 molar copper sulfate. Well, it says copper 2 sulfate, but that's what copper 2 sulfate is, right? Plus 2, minus 2.
Okay.
So if we want to know how much, so what does 1 molar mean? What's the meaning of this? What's the capital M stand for? When I say molarity, what does that mean?
Mole? The mole?
It means mole,
Yeah.
but that's not the same as molar.
Molecule?
What's the difference between mole and molar? Mole is an amount, and molar is a concentration. This is a concentration right here. So what does it mean? Part of it is mole, yes, but it's a concentration. It means mole per something. It's the amount of moles in a liquid. So what do we measure liquid in? What sort of units do we measure liquid in? What's the standard, like the standard metric unit for liquids?
Standard for
What do you measure? Like tonight, what did we measure our liquids in? What was the unit we used?
oh,
What does that stand for? What is it?
is that milliliter? Sorry.
Milliliters, right. And milliliters is 1/1000th of a liter,
Mm-hmm.
right? So 1 molar just means 1 mole in 1 liter. That's all it means. So if I have 1 mole in 1 liter and I used 100 mils,
Okay.
then all I need to do is convert my 100 mils to liters and I can figure out how many moles that is.
Okay.
So then I would just multiply that by 1 liter is 1,000 milliliters. And I cancel liters. I cancel milliliters. And all I'm left with is moles. So it's
Yeah.
just 100 over 1,000.
Okay.
100 divided by 1,000 moles, which is how much?
Wait, I didn't get. Never mind. I was in the phone. It's 100.
Divided by 1,000.
Okay. 0.1.
0.1. There you go. So you have 0.1 moles. That's how many moles of copper sulfate you added to your reaction. 0.1 moles. Because you added 0.1 liters at 1 mole per liter. So it's the however many liters there are of this is how many moles you have of this. So if you added 1/10 of a liter, you added 1/10 of a mole. If you added 100th of a liter, you added 100th of a mole. So that's what makes this particular bit of math a little easier than the aluminum. The aluminum we're going to need to figure out. We need to convert grams to moles and all that stuff. But for things in solution already, we don't need to do that. We just need to figure out our volume and what the concentration is. And this concentration is really easy. 1 mole is 1 liter. So 1 to 1. Okay.
Okay.
All right.
Thank you, Professor.
No problem.
What about for the moles of aluminum? Is it just 1? Because I got
Why
1
would it be-
mole
Why would
over
it be 1?
because it
If you
said
had 1.5 grams of aluminum, how could that be 1 mole of aluminum?
oh wait.
You need to convert grams to moles. If you don't know how to do that by now, I'm seriously
I'm I was
bad
just getting
teacher.
kind of confused. So you use whatever you measured and then you just convert that to moles.
Yeah, Mhm.
Okay.
yeah. So 1 mole is, what was it, 20?
I got 26.918153.
Yeah, 26.9 grams or so. Yeah, use as many significant digits as you can. And that'll give you moles. right?
Oh, okay.
So grams of aluminum, grams, you're left with moles. Yeah, aluminum is incredibly light metal. It's one of the reasons why you make airplanes out of it. It's only 26.9 grams per mole. So it's very, very light. Not quite as light as magnesium, but pretty light. All right, everyone.